Okay. It looks like a few people have to accept that the session is being recorded. And it is 6 o'clock, 6 o'clock my time here in Melbourne on the dot. So I'd suggest we'll give it a go. So Francois Gauthier is our first presenter. And I've got too many things on my screen, so I can't really see the title of your presentation. But I'll leave it up to you, Francois, to share the first slide and let us know what you're up to. So all yours.
Okay. Good. Can you see my screen?
Yes, we can.
Great. Okay, so thanks for joining. This talk is about runtime prevention of deserialization attacks, which is likely the most critical flaw you've never heard about. So for a bit of background, untrusted deserialization exploits were introduced in the OWASP Top 10 in 2017, and in 2021 they were merged in the larger injection category. And they are typically, when successfully exploited, extremely critical. They lead typically to remote code execution, full control, full takeover by the attacker. And one of the issue on the defense side at the moment is that the state-of-the-art approaches like deserialization filters and the JDK require you to block or allow individual classes without any context. And this is extremely difficult. For example, the hash map in Java is commonly used in deserialization chains, but that doesn't mean that hash map in itself is malicious. So what we're suggesting in this paper is to use Markov chains to reason about the context in which a class appears in a deserialization chain. So when I'm saying deserialization chain, this is because this is how the deserialization format works. If you have an object graph, like at the top of my slide, and you serialize it to a persistent format, like the Java deserialization format, it will look like basically a sequence of classes written to a byte stream. And so then the converse process, which is deserialization, will read that byte stream and reconstruct the object graph as it goes. The issue is that if you have some classes that override certain method like readObject, then it might lead to an attacker controlling the code that is executed as the object graph is reconstructed. In this case, basically the command that's contained in the string field here would be executed, and the attacker can control that by crafting a string. And so the hypothesis we have in this work is that by looking at the sequence of classes and, more importantly, their features, we will be able to distinguish between benign and malicious deserialization chains. So what we did in this paper was to review known attacks that are in an open source repo called YSOSerial, and we came up with a simple set of features, a set of Boolean features that I won't go through today for lack of time, but it's all in the paper. So basically what we can do is, given any Java class, we can do some introspection and abstract those classes as a set of 8 Boolean features, which then become the states in our Markov chain. And a Markov chain is really just a probability transition system with states and probabilistic transitions. And so then when we are reading classes from a stream, it's really just as if we are transitioning from a set of feature to another one. And so the idea in this paper is that we build 2 Markov chains, one that captures benign deserialization chains and one that captures malicious deserialization chains. And so then at runtime, as deserialization is happening, we look at the probability that the chain was emitted from the malicious Markov chain versus the benign Markov chain. And then if the probabilities start to differ significantly, we can then make a call and say, okay, this is likely benign or malicious. The issue is that estimating those transition probabilities is tricky. The classic way of doing it is just by looking at the actual frequencies in your data set. This works well with large data set, but deserialization is quite an uncommon operation, so we tend to have very small data sets. So what we did instead is to use a Bayesian approach, where you are conducting basically statistical simulations to build a collection of Markov chains that characterize your data well. So these are the results. We did this study on an industrial system called WebLogic Server, and we compared against the Wiseau serial exploits. And so you can see that using the Bayesian approach, we managed to achieve a precision of around 90%. That's compared to the classical empirical approach that only achieved around 73% precision. However, this has a cost, so the training time is quite high. Note that at runtime, though, once the Markov chains have been built by Bayesian inference, the checking is actually really fast, so in the order of milliseconds. And this T parameter here is really just the size of the confidence interval. So this is basically, as the confidence interval is larger, we become more conservative, hence slight drop in precision and increase in recall. To conclude, I also just wanted to say we took a deep dive in our false positive. We looked at those chains that were falsely marked as malicious, and we discovered that they actually fall in different categories that are typical targets for deserialization attacks. So this is not to say that these are not false positives, but they definitely have the characteristics that attackers typically look for when they are crafting malicious gadget chains. And this concludes my talk. Thanks for your attention, and I'm looking forward to your question.
Okay, thank you. Do we have any questions from anybody in the audience? There doesn't appear to be anything in the chat. Otherwise, I'll ask a quick question. You mentioned the hash map in the earlier parts of your presentation. Can you elaborate a bit more why that is a problem with deserialization? I have an idea, but I may be wrong.
Yes. So deserialization, for those who are familiar maybe with return-oriented programming, is very similar. So in the context of hash map, what is happening is as you are reconstructing the hash map from a serialized stream, you will call the hashcode method on every single object in that hash map. And that gives a very interesting starting point for attackers to then jump into something else. So then the game becomes of looking into all the classes that are available in the class path in all the libraries for a class that overrides hash code with some interesting code. And so from there, you know that hash code will be called as the hash map is being deserialized, which might lead you to jump into something else. And so this is how you kind of jump from one class to another. And this is a very, very, hash code is overridden several times. And so that's a huge state space for attackers to explore. I hope that answers your question.
Yeah. Would you then use something like a tree map instead of a hash map to avoid that problem? Because from a functionality perspective, they're both maps, right?
Unfortunately, tree map suffers from a similar flaw, where tree map will call compare on each of the elements, and then you can play the same game. As soon as you find an object that overrides compare, you can shove it into the tree map, send it for deserialization. So it's tricky.
So does that imply anything that in the deserialization calls a method that you can overwrite and do whatever you want with is a problem? Or does that go too far?
It's a potential problem. The whole game is really that you cannot write your own code. You have to use code that's already on the victim's class path. So you have to find popular libraries. You have to find classes that override interesting method and see if you can stitch them together. So you are not allowed to write your own stuff, but yes, the moment something is deserialized that calls very commonly overridden method, you are taking a risk, basically.
Okay. Do we have any other questions? Doesn't appear to be. So thank you thanks very much for your presentation, Francois. And I'm sort of now very keen to read the paper a bit more thoroughly than I've done so far. So thanks a lot. So can we give Francois a quick round of applause, either virtually or in real terms? And I'm now handing over to Michael, who is next in the line for the presentation.
All right, can everybody see my screen?
Yep, we can. All good, so all yours.
Okay, thank you. Hi, everyone. My name is Michael Schröder. I'm a PhD student at TU Wien in Vienna, Austria, where my PhD advisor and co-author is Jürgen Zito. And I'm going to present to you Grammars for Free, our vision toward grammar inference for ad hoc parsers. So you probably all have written code like this before. This is just a simple Python expression that turns a string of comma-separated numbers into a list of integers using standard functions like split and map and the Python int constructor. This is what we call an ad hoc parser. Doesn't use any particular parsing techniques or frameworks, but it's clearly parsing a string according to some kind of implicit grammar. These parsers are everywhere, right? Anytime that you do anything with a string, whether you split it or you slice it or you just trim white space, you're in fact parsing the string. And while you most definitely have written an ad hoc parser yourself at some point, you might not have written down a formal grammar for your parser. In fact, I'm pretty sure that you haven't, at least not for these like small pieces of code, right? Now here are two equivalent grammar representations for this little example. And these are finite but complete formal descriptions of all the accepted inputs of the parser. Basically, all the values that this string S can have without the program going wrong in some way. And there's an analogy here with types. Just like types, grammars are a form of a parser without an explicit grammar is very much like a function without a type signature. So it's probably still going to work, but maybe not in the way that you expected, because you won't have any guarantees about it before you actually run the program. Whereas if you had the type or the grammar, you could reason about the program's behavior. Now, types have one significant advantage over grammars. Most type systems offer a form of type inference, allowing programmers to generally omit type annotations because they can be automatically recovered from the surrounding context. Now, what if it was possible to also infer grammars from the surrounding context? What if we could infer grammars just like we can infer types? And this is exactly what we want to do in our work. So here is an overview of the end-to-end grammar inference system as we envision it. Now, obviously, in the short presentation, I don't have time to go into all the details. You can find more in the paper and the long-form video. But the basic idea is that we take some ad hoc parser source code written in any general purpose programming language, like, for example, Python. We carefully simplify it into an intermediate representation, which is basically just a domain-specific language for parsing. And then from this intermediate representation, we infer a language model, very similar to how one would infer types for a program. And in fact, we're using some of the same techniques. And then from this language model, we can generate grammars in various textual or visual forms. And this kind of automatic grammar inference would enable a whole range of new applications that haven't really been possible before. So first off, these inferred grammars could be used as interactive documentation, you know. So documentation that is always up to date and that's closely linked to the underlying source code, right? So this is different than a grammar that you would write by hand. Because with inferred grammars, you could imagine, for example, an IDE plugin that shows you the implicit input grammar when you just hover over a function definition. And it would maybe even let you drill down into individual production rules or non-terminals in the grammar and trace them back to where they originate in the source code. What you could also do is something that we call bidirectional parser synthesis, where if you combine this novel grammar inference with existing parser generation techniques, you can enable semantic program transformations. So you could, for example, do grammar-based program sketching, as illustrated on this slide. So you start out with an incomplete program, a sketch. You use grammar inference to get an initial grammar that the user can then manipulate and refine on the level of the grammar. And then from this refined grammar, we could synthesize a refined program. Of course, you could, loop this back and then more and more refine this program just by manipulating a grammar. Finally, we also envision some really cool implications for code mining and learning, because a grammar is basically an equivalence class over concrete implementations. So it allows us to group together different parser implementations with similar semantics. And we can use this to build a grammar-based code search, where the user can query for certain production rules or grammar patterns, and the search engine then returns specific instances of implementations of these grammar rules. And then if we add a history component to this, we could watch how grammars change over time, enabling a kind of semantic change tracking. So you could imagine a build bot that augments the code review process with current and historical grammar information, so that the program is alerted when a code change they commit introduces potentially a change in input grammar. And we are hoping to realize this end-to-end grammar inference system and some of the applications that I just described, at least as prototypes. And to this end, we're working on a number of related projects. You can find more information about these in our paper and the long-form video, which also include more background and our intuitions behind the inference process and its feasibility. So with that, I want to thank you very much for listening to this short presentation. I'm really excited about the possibilities of the system, and I want to invite anyone to collaborate with us to realize this vision of grammars for free. So thank you very much.
Thanks very much, Michael. Okay, so we've got a question in the chat. Typical grammar question. Sorry, couldn't help myself. Whether you wanted to infer a context-free or a regular grammar.
Yes, a good question. So in general, the idea of the system is to be well, we're limited basically by the limitations of how powerful our inference can be, right? So we have, I mean, there are some very fundamental limits as to what we can infer, right? Basically, anything that's up to deterministic context-free grammar, so that's kind of a little bit lower than context-free, that's basically anything where you could write an LL1 parser for it. That seems to be something that we could feasibly infer. Now, practically, it might be, you know, maybe even a little bit below that, or it might include even some context-sensitive features. I mean, you know, beyond the classic Chomsky hierarchy of like, you know, regular, context-free, context-sensitive, and so on, there are vastly more classifications. And in practice, the kind of grammars you see, especially in these ad hoc parsers, you know, very often you just have some regular or even sub-regular fragments, but sometimes you have something that is, you know, just about context-free, but in a very specific kind of deterministic way, and often you even include like context sensitivity, but in a limited way. So hopefully the system. So what we want to do is we want to infer the most kinds of grammars that are used in practice, you know, and to really figure out which grammars are used in practice, we are currently conducting some kind of mining studies to figure out, you know, what's the scope of our system. But in general, yes, we want to go beyond just regular languages.
Okay, I hope that's the question. Yeah, that would have been my context. Sort of to follow on that, how complex can those? It sort of, for me, it looks like you're having some form of regular expression type combination in your code, and that from there you infer a grammar. How complex can this become before you have to say, sorry, this is now beyond what we can realistically do?
I mean, honestly, we don't really know yet. I mean, the current approach that we're doing is in the backend built on a refinement type system, and as part of this, it discharges some verification constraints to an SMT solver. And so basically, anytime you involve an SMT solver, it's like it might, you know, not be able to solve your problem. It might get too big, too complex, or just not feasible. In practice, from, you know, the parsers that we've seen, that we encounter in practice, I would assume that most practical things we could infer, but there could always be, you know, some edge cases or some things where it's just deviously tricky to do it for particular cases. But in the end, you know, we're limited with all these like steps in our inference process, like for example, the power of SMT solvers, you know. So it's hard to precisely quantify yet. I mean, that's something that we still need to do.
Mm-hmm. We've got another question. What about implicit assumptions by the underlying programming language with respect to scanning? So \n as an example.
That's a good question. So as part of this process, we need really to have precise specifications. Like for each source language that we want to be able to infer grammars for, we need to have precise specifications of the kind of string primitives in the language. So for example, I don't know, the Python, you know, split, you know, function or some kind of Python, you know, trimming or a white space function or something might have a very particular way to deal with, like, you know, scanning /n or something. Another language might have a different way. And of course, unfortunately, not all of these are maybe documented, and they might even change slightly between versions. So that this is just some kind of engineering effort almost, or I guess specification engineering that you have to do. And this is part of the input of our system, right? So for each language that is an input language into the system, we have this library of specifications for these string primitives. I mean, you only have to do this once, but yes, it is a significant effort to come up with these initial specifications, obviously.
Now, sort of along those same lines, the one language I tend to use when I have to parse text and do some simple manipulations is Perl. It's not that frequently used anymore these days. I tend to be able to write regular expressions a bit more easily in Perl than in Python, but Perl has a lot of implicit stuff in regular expressions. So anything like that, you would have to have the precise specification how it works, right?
Yeah, exactly. I mean, it is interesting that like regular expressions, I mean, I think most languages, at least, also even Python and JavaScript, they have like their own regular expression stuff, which are not precisely regular expressions, but have a little bit of an add-on, and yeah, that is kind of tricky. I mean, as far as Perl goes, yeah, I mean, we really haven't planned as a part of the initial kind of set of languages we support, just because I don't, even the language itself, I think, if I remember correctly, is like a parser for Perl is kind of there was some incompleteness kind of or unprovability theorems that some people came up with a few years ago, I think.
Yeah, well, you can do some nasty little things in Perl. You can do that in Python as well, by the way.
I'm sure.
The moment you use the meta level, you don't see anymore what you're actually going to get.
Yeah, I mean, we will definitely have to scope it like down to a practical level and have just a kind of a commonly used subset of all these languages, and beyond that we say, sorry, but if you write such complex programs, maybe simplify a little bit.
Yeah. Okay, then, Michael, we're running out of time, so thanks very much.
Thank
you. A virtual or real clap for your interesting presentation. So Dominic is next, so all yours, and hopefully technology will work as fine as for the first two presentations.
All right, can you see it? Hello?
Yes, we can. Yep, we can hear you and we can see it.
All right, I'm going to start the timer. Let's go. Hello. Yeah, I'm Dominic. Asynchronous call graph for JavaScript, National Taiwan University, all that. Yes, perfect. All right. So why do we do this? Basically, it's very simple. I envision this as a software developer to basically give me and visualize automatically certain connections in my program, because, well, it's very difficult to understand our programs. And especially when it comes to asynchronous behavior, we even did a survey a long time ago, and it turns out like asynchronous behavior is like the most feared of all the things, especially on the junior kind of like level. And I myself, I was thinking that I don't really know what's going on in my programs, because there's all these things that are implicitly going on because of, well, what is asynchrony? It's a way to produce concurrency. And concurrency usually, well, if we use threads or we use some sort of like more traditional approach, is very explicitly communicated. But in JavaScript, everything is implicit. So that's really why we wanted to build this thing. And it should automatically basically find all these things that schedule asynchronous, well, behavior. And then it finds all these pieces of code and connects them on this on this network of virtual threads. That's what I call them. And I really wanted to make it visual and also interactive. So everything you see is not only a visualization, but you can also click into it and it takes you to the code. And it's all integrated in VS Code. So it's working on a lot of real world projects as well. Ultimately, my real goal is to improve interactive debuggers. It's something that just has not been done in such a long time. And even Lieberman in 1997, he pointed out, well, things haven't really changed in our debugging and like these tools that help us with program comprehension. And he was saying that in 1997, he said, oh, for 30 years, nothing has changed. And now 25 years later, little has changed still. So it's like 55 years of little innovation in terms of interactive debugging. And that's really where I want to kind of like get my foothold in. I personally, but also, of course, we as a team. Yeah, so that's okay. That's it. There we go. So let's look at an example. We have here, I don't know if you read JavaScript code, but on the left, we have this sort of like way of saying, well, after F1 is done, and F1 might actually represent a subgraph of computation. It's not just maybe just F1 itself, but F1 might itself dynamically nest more things to do that will then basically all have to be done in order for sleep 1 second to happen next. And then after sleep 1 second, we do F2. And we are capturing this over here in this graph. So this is the graph, this is the code. And this is like one thread. This is ensured by the semantics of promises and async functions to execute basically serially. And then the next thing is, well, here there's G1 followed by G2. and then H1 followed by H2, but all three of them at some point in time are actually working concurrently. And just looking at this code for the first time, you might not know that. It would be very difficult to know that, especially since you don't even know how long certain things take. And so this thing is, well, it's built on an omniscient debugger, so it is all dynamic analysis. It's not static analysis. And yeah, we just can easily see all these things that are going on concurrently. Also, it takes care of async functions. So main has 3 awaits that are also prominently featured over here. Promise all is being taken care of. It can already support a lot of little things. There we go. Also, it's being forked from the entry point, because over here, there's like from the entry point, we're calling this function main, but we're not awaiting it. So because we forgot to await it, so it's a fork. All right, let's look at this here real quick. Given this function, we do something f, and then we ultimately do something g. We somehow nested in a promise. Well, why would we do that? Well, because this is basically some sort of async function. F is some sort of async function. So if we use it in the right context, G can be serialized in a sort of like this virtual kind of thread. And so when we call F like this, just like that, what happens is that G will get forked off. So if G is a subgraph of computation, it might do all kinds of different things concurrently with the other instance of G that is being run, because, well, it's executed twice. So this forking is to encapsulate exactly that. Another example, well, we just haven't forgotten to await. We have not let our promise dangle, and as a result, we have this nice little serial flow of execution right there. All right, and well, there's this other thing that we are also taking care of callbacks for some reason. Well, to be honest, well, there is just so much asynchronous callbacks still in JavaScript code. That was one of the things we found, that promises and async functions are not used all that much. So I also really wanted to put in callbacks, but the problem is you cannot easily understand what the behavior of asynchronous callback scheduling behavior is. And here's an example of how that can be ambiguous. So for example, here are 2 different asynchronous callback semantics, which will lead to entirely different behaviors. And we are not able to find this behavior. This is a theory, but we cannot determine it. That's why we have to resort to heuristics to deal with that. All right, that's it. Yeah, my time is up. Thank you.
Thanks very much, Dominic. We don't seem to have any question in the chat. Then I sort of try to step back a bit from your work. Where do you think that will be useful? So you say you're creating an interactive debugger on top of VS Code. Who do you think will be the target audience, and what should they be able to detect? Ultimately?
Yeah, the original intent was that it can be used on a professional level. I myself, as a professional software developer, I'm certainly looking forward to using this more. I have been using it a little bit, but of course, in order to make things really work for the real world, that's an entirely different process. If I have funding, then I can do that. If I don't have funding, then I might have to scope it down again, right? Just like Michael and I guess most people here would have to suffer from similar issues. Now, one thing is to simply say, well, let's target the novices. The novices, or I would say at least the intermediate learners, would very much benefit from such a thing, because they can interactively kind of like deal and look into the behavior of their code. Oh, this is my code. This is the behavior of the code, and maps to one another. And you can click into it, and you can see the connections between everything. So ultimately, we might have to just scope it down to novices. I don't like the idea, but this might be a more realistic kind of like assessment.
Mm-hmm. How do you deal with race conditions? Because the moment you've got asynchronity, that can very quickly throw things out, right?
So, well, I mean, our algorithm is not affected by that, and our algorithm just highlights it for you. So if you have forgotten to await your promise, or you have scheduled promises in an awkward kind of way that leads to potential race conditions, the fact that you see a fork instead of like basically being on one thread, it's being moved off into the other thread, you see the potential for race conditions. So the race, it's basically a tool to show you potential for race conditions. And in fact, we have, like in the paper, you can actually see a few examples of that, where, for example, the async library, it's called async, which has an async queue. And so you give some stuff, you just put some stuff into the queue, and then it makes sure that whatever you put into it will then asynchronously be executed over time, but serially. And there was a bug in that where the where the ACG just very quickly shows you exactly, oh yeah, that's definitely buggy behavior. And you can click into it, and just like 2 more clicks, you can find exactly where the bug was coming from. Yeah.
Mm-hmm. So in other words, what you just told us, that there is some real value in debugging things that otherwise may be a heck of a lot harder to find out.
Yeah, I would have thought. There's certainly a lot of value in this. I see a lot of potential. Of course, the ACG is just one of the more like advanced technical innovations on top of a rather complex system of other features that we are also offering, such as a synchronous call graph, as well as data flow and other features. If you combine them, then I think you get the value you need for a very large set of all the debugging tasks.
Mm-hmm. Okay, then. Well, thanks very much, Dominic, for your presentation, and a big clap, either real or virtual, from all of us. Jose Miguel is next. So if you can get ready and share your screen, that would be great.
So, can everybody see my screen?
Yes, we sure can. So the floor is all yours.
Okay, okay, thank you everybody for coming to the session. My name is Jose Miguel Perez, and I'm going to present our paper, Lowering Barrier to Application Development with Cloud Native Domain-Specific Function. Creating and customizing application remains an expert task. People that don't have knowledge, they are comfortable using content management like apps, such as blogs, social media, all this kind of tools. But if they have to create an application, they are not comfortable using ADAs or using frameworks or this kind of stuff. In order to allow them also to create application, one area that have done a lot of improvement is the domain-specific approaches and DSL. Using these approaches, non-technical users, they can create abstract-level behavioral models that then, using domain-specific approaches, can generate the actual code for a target platform. However, these techniques still have a big gaps and challenges. For instance, they have to deal with multiple technological stacks. They have to deal with heterogeneous clients, with multiple development tools. They have to deal with also different user interaction, because it's not the same to create an application for a voice-based platform such as Alexa than create an application for a smartphone that is screen-based. And still, there is the question about how to provision and how to monitoring these apps. In order to solve this problem, in our approach, non-technical users still create these abstract behavioral models, but we don't generate code about, from this abstract behavioral model. They are directly executed on the cloud. And then what we propose is a coordination mechanism that completely decouple what is being executed in the cloud and the target clients. And this allows us to have generic clients. This is because in this coordination mechanism, what we interchange between the cloud and the client is never graphical information on how do the clients need to interact with the user. What we interchange is just the information that need to be displayed to the user, the information that need to be gathered from the user, some constraints and some values. And it's the responsibility of the client to adapt the interfaces to show the information to the user or get the information that is needed to continue the execution. Here we can see an example of our behavioral models, and the boxes are activities that come from a library of activity that the non-technical user can use, and the arrow represents transition between those activities. In our coordination mechanism, as we can see here, we keep executing everything in the cloud up to the time that the cloud determines that there is a user interaction need. In this moment, the cloud connects to the client coordination mechanism, sends the information, and the client, has the responsibility of render the interfaces and interact to the user in order to show or get the needed information. Once the needed information is collected, it's sent back to the cloud coordination mechanism who continues the execution. In order to evaluate our approach, we have created a prototype, and we also did a user study. With our prototype, we have developed a well-known application, and we have compared our implementation with the existing implementation of the same app for both for front-end and for back-end. And as we can see here, in general lines, we needed less line of code to develop the same application for front-end and for back-end. And then we also introduced a chain, and we wanted to see how difficult, what is the effort to introduce this chain in the existing implementation and using our approach. As we can see here, for backend, we needed to modify so little line of code. And in the case on the front end, because our clients are completely generic, we don't need to modify any line of code to introduce this chain. For our user study, you can see here some quotes of the participants. And we can say that in general lines, we believe that our approach help to non-technical user to create application. So that's conclude my presentation. So if you have any question, I'm happy to answer them.
Okay, thank you very much, Jose Miguel. Sort of to kickstart the discussion off, what type of users do you target the work to?
For now,
no idea what a computer program is. They may not be able to do what you think they could be able to do.
Yeah, I mean, our experiment, our user study, we did the user study with students, with first year students. Yeah, they do have some knowledge. Some of them, they have knowledge in HTML and some programming language, other less knowledge. But yeah, in general lines, yeah, we can say that at least a little bit at least to know what is one activity and what means this transition, you need to have certain, especially if you want to do something complex. But we believe that we are lowering the barrier to also allow people with less technical knowledge to do this application.
So Raviva tried to make then a link to the previous presentation. So, okay, I have a high level representation that I can create something like an application, and it doesn't work. How do you help me to figure out why it doesn't work?
For this, what we have in our prototype, what we have created is a mechanism where while you are putting boxes and where you are connecting, you are able to see the inputs and the outputs. You can see like in live what's happening with the flow that you are creating. So we help that this, we think that this help also to see what's happening.
Mm-hmm.
And also for the, another advantage is that because the clients are completely generic from the first beginning, from the first moment, while you still have an empty flow, an empty graph, you are able to see result directly in the final application, either if it's not finished. So we think that it's also really easy to debug what's happening, because you are seeing, even if your functionality is not finished, you are able to see the inputs of the kind of interaction that you are generating.
You said that the client interface is completely generic. Can you tell us a little bit more about that generic client interface?
When we need generic is, for instance, these clients are already available and they can adapt to any interface, because what the cloud sends is, okay, I need you to show this information to the user, and I need from the user to get this particular information. So imagine that it's an application for list in our example, you can see in the paper, we are creating an application that lists a set of articles, and the user select ones, and in order to get more details, or in order or if you want to get more, if he is pagination. In this particular apps, if the target application is a skill for Alexa, what we send is the list of articles, and we say to the user, you have to show. We say to the client, this is what you have to show to the user, and we need to get one particular if you want to give detail. And in case of Alexa, the code is ready to detect this and to say, okay, I have to render voice and I have to tell this to the user. And in the case of you are in an application which is a smartphone application, the code is ready to, okay, get this and generate the page for you to select. But it's true that these generic clients in the first view is the same for everybody, so it looks really similar, but we also put it some points of extension, so people that have knowledge also can customize them in order to maybe look up to have a different look and feel, or to have a different visualization, or even a different behavior. But once this client is also customized, it remains the same. If you modify the application, I mean, if you modify the behavior at some point. I don't know if this answers your question.
It does to some extent, but I'll probably have to read through the paper a bit more carefully there. But anyway, we're slowly running out of time, so thanks very much, Jose Miguel, for your presentation.
Thank you.
And a clap from all of us. So Jing Zhang is next. If you can share your screen, Jing, that would be great. Thank you. It's coming.
Okay.
Well, now we see ourselves infinitively. Okay. Yep, all good.
Hello, everyone. I'm Xin Zhang from Peking University in China. The title of our work is Towards Bidirectional Live Programming for Incomplete Programs. This is a joint work with Zhenjiang Hu, also from Peking University. To combine the intuitiveness of direct manipulation on the output with the abstractness and repeatability of text-based programming, researchers have developed many bidirectional live programming systems, which can not only allow developers to see continuous feedback by evaluating programs, but also allow them to directly manipulate the output to automatically synchronize the program. However, there is a big limitation. They cannot deal with incomplete programs where code blanks exist in the source programs. In practice, developers tend to program in a way where they skip some parts by leaving some code blanks during programming. It would be practically useful if even when the program is incomplete, developers could still directly manipulate the output to automatically synchronize the program. Fortunately, OMA has made nice progress in unidirectional live programming for incomplete programs. They model the incomplete programs as expressions with hosts, which denote missing expressions. They track the evaluation states, called closures, that is, variables with their bindings, that can be accessed by hosts. With the technique of live programming for incomplete programs, what we need to do is to make this technique bidirectional to achieve the goal of bidirectional live programming for incomplete programs. Let me show you an example. F is a function which concatenates X with an unknown expression represented by a red question mark. The final expression is a tuple where the two elements are function calls that apply F to XE and 2021 respectively. The output is a tuple of two hosts named *1 and *2, which are equipped with hold closures. For example, XE is bound to the variable X in the closure of host *1. Both the output values and the hold closures allow modifications. For example, if we change the binding of X from 2021 to 2022, then the program updates correspondingly. On the other hand, if we change the two hosts to two determinate strings, our system will generate requirements that hosts must meet. Therefore, two requirements are added to the whole bindings table, which describes the output values of evaluating the whole when X is ICSI or X is 2022. Interestingly, we run the program with whole bindings again to get the output that we previously changed the whole incomplete tuple to. This means that our system satisfies round-tripping properties. Here is our tool called bidirectional preview. The input is the code written in the editor using our language, and the whole bindings. The output includes the HTML output and the whole closures. The eval button performs forward evaluations, and the uneval and update button performs backward evaluation. Consider the task to implement an HTML table to record the birthdays of classmates as follows. Developers can implement the logical framework first and set the details to host. For example, the spacer and the color variables are set to host. Evaluate this incomplete program. The incomplete prototype is shown on the right, where the second column is missing and the first and the third rows have no color. We can edit the content. For example, we changed the star 2 to September 5th. Then we got the requirement that for the first whole. We can also edit the colors. For example, we changed the color of September 5th to light yellow. Then we get the requirement for the second whole. Evaluate this incomplete program with two whole bindings. We can obtain a complete output that we desired. To sum up, we propose the first programming framework to support bidirectional live programming for incomplete programs. In particular, we carefully formalize a bidirectional evaluation for incomplete programs which satisfies round-tripping properties. For theoretical details, welcome to read our paper. We also give an efficient implementation of the bidirectional live programming framework as a concrete tool called bidirectional preview. The code and more examples can be accessed through this URL. Welcome to use our tool. That's all. Thank you.
Thanks very much, Jing. Do we have any questions from the audience?
Well, I was typing, but I can talk.
Yeah, go ahead.
So one thing that strikes me is that this bidirectional framework might actually be useful to accommodate a team of two. If you have maybe someone who's more versed in programming and someone who's more versed in user interface design, it seems like it would be a really good way for them to communicate, basically.
Yes.
Is that something you foresee, or did you have like one person using both sides at the same time in mind? So basically, what are the use cases you foresee with this?
For professional programmers, they can text-based programming, and for designers, they can use the prototype window. And I think it can be easily used by only one person too, because when he or she is programming, she can use the developer can use the tool to observe the evaluation state of its program, of the evaluation of the program, and they can also edit the incomplete output and the observations through the evaluations. So I think the target users can be the professional programmers or students or designers.
We have an very interested guest at Dominic's end, I can see. Just sort of to follow on from that question, Jing, what would you do if you create a conflict? Say you have a hole that will generate two different fields at the user end, and you edit them in an inconsistent way. Would your tool give the user a warning that they've just done something they shouldn't have?
Yes, there may be the situations that the updates are inconsistent, and we adopt a heuristic method to tackle with the conflict. We randomly select update and update the program consistently, and after re-evaluating the program, the updates on the output will be consistent. And we call this three-way merge. Three-way merge for different or inconsistent updates.
All right. Yep. Thanks very much for that. So we've got 9 minutes left for the final presentation and some questions. So thanks very much, Jing, for your talk, and a clap from all of us. And Dominic, maybe your co-worker can give a clap with the pause as well. And last but definitely not least, here we go. We've got Stefan to give the last presentation of the session. So all yours, Stefan.
Thank you very much. So my presentation is not so much about new technology. It's about evaluating some existing thing. The presentation, the paper is quite a complex title. It means just we compare whether or not we should use the Stream API or whether we should use collections, or if we should handle collections in a traditional way using loops. So what do we speak about? Let me give you an example. So this is the way how we traditionally iterate over a collection, and this is what traditionally is being taught at universities or different schools. So you have a person collection and you build a for loop, and then you have some filter criterion. In the example here, it's person age is larger than 21. And in case this criterion matches, you add it to a result collection, and then you do something with the result collection. If you do the same thing with the Stream API, the code looks slightly different. So you no longer have an explicit loop. Instead, you have this implicit loop, and you have this filter method, and you're passing a lambda expression to it. And the general question for us is, well, does it actually make sense? So should we prefer the Stream API over loops? The Stream API definitely is a more modern form of collection handling, and it is more in the spirit of declarative programming that we find more and more in mainstream languages. Still, the question remains, does it actually make sense? To ask this question, we should take a look into the related work, because we have an ICSE paper in 2016, which actually says lambdas seem to be rather a burden than a benefit for developers. So it was a randomized control trial in 2016, where we measured drawbacks in the development time of iterating a certain collection in using lambdas when you write code on your own. And the question that we have here in the given presentation, it's so much about writing code, but reading code and giving answer what the code actually does. So what did we do? So we give people a certain code snippet, which is either formulated using loops or the Stream API. And then we have on the left-hand side, this is here, you have the input of this method, and you as the participant of the experiment, you have to choose from the list, right, what the output should be. So you choose from a list, and then you confirm your choice. And when you confirmed your choice, then we stop the time measurement, and then in the end we evaluate how much time it took and how many errors people did. At the end, we have some collection of subjective ratings. I'm sorry, it's in German here because the tool is written in German. It simply just says it's asked participants, how good do you think you were, how fast do you think you were, and did you like the code? And you can always answer from 1 to 10. So let me just skip. Maybe let's say what we were. So we just had 20 volunteers, 10 master students, 10 professional developers, and we gave them all together 7 programming tasks. And it took it's as a result, we found that when we just speak about the means, people were always slower using the traditional loops, which was astonishing from our perspective, because we had their code, which was from our perspective quite trivial to understand. People were still faster using the Streamer API to understand what the code actually does. And more interesting, even the number of errors in the responses was less in the Streamer API in comparison to loops. When we speak about what is the difference between loops and the Streamer API on average in the whole experiment? Loop took about 78% more time to answer the question. So spoken in absolute numbers, we speak here about, as you can see here, something like 100 seconds against 200 seconds or whatsoever. Okay, so what is the, maybe just one quick thing, participants were able to identify that they felt that a positive impact of the Stream API in comparison to loops. So it's not only a matter that we measured it in terms of times and in errors, it's also that participants were able to subjectively perceive a certain value in the Stream API. So from our perspective, the big conclusion is we know from other experiments that lambdas have a drawback. On the other hand, it looks like we have a benefit when we just speak about reading code. So thank you very much. I think I was about 30 seconds longer than that I was intended to.
Your mic is off, John Guy.
Sorry, it had to happen at some stage, right? That I forgot to turn my mic back on again. Thanks very much, Stefan. Why do you think your subjects felt that using the Stream API, that's easier to read than using the more traditional for loops? Did they comment on any of that?
Actually, not really. We got certain, but from different experiments, we got certain other feedback in terms of variables that we controlled, and some other experiments that we did seem to suggest that a problem in the traditional loop is the loop variable. So just finding the loop variable and then doing the connection between the loop variable and the for example, just the filter, which is 1 or 2 or 3 lines below, seemed to maybe not to confuse them, but it just takes more time to jump here and there with your eyes to understand this variable here and this variable here. They are both connected, speak about the same thing.
Okay, so we've got 2 questions in the chat. So question number 1 from Oleg is, can we call a stream truly declarative? How do you answer that, Stefan?
Actually, well, maybe these things are slightly more political questions. Like, so if I have, from my perspective, if I have no explicit ordering specified in terms of the API, from my perspective, we already speak about a declarative operation. I mean, when we say that SQL is a declarative language, people typically say at that point, yes, because the single operations that come one after the other are not explicitly declared. So is it declarative? Well, I think kind of.
Do you think, and that's sort of a follow-on question from me on that, you can do less things if you have to use a than if you use a loop, and that may make the loop a bit more harder to understand.
Actually, so okay, I can. This question is more about my personal belief. So, so the thing in 2016 was the kind of iteration was different, and I think the kind of code that we now show